I kindly request the professors to take off their caps. I open this session with a prayer. May the spirit of wisdom and mercy grow and blossom in all of us. Please be seated. My pleasure to welcome you to this academic session on the occasion of the public defense of the dissertation titled Correcting Selection Bias in Non-Probability Samples by Pseudo-Weighting. And the candidate is An-Chiao Liu. We look forward to your defense and your presentation. As you see from the title, but also from the content, it's a very impressive subject, so I'm very happy that we have an expert committee today to serve you with some interesting questions. And I will introduce the PhD committee one by one later on in the session. And I also welcome the committee, also welcome the two supervisors, Professor Dr. Katrijn van Deun and Professor Dr. Ton de Waal, both from the Department of Methodology and Statistics in our wonderful school. I'm Mark van Veldhoven, by the way, the Dean of Tilburg's School of Social and Behavioral Sciences, and I'm acting on behalf of the Rector to chair this session today. Before we start the defense, I would like to give the PhD candidate the floor to give a concise summary of her research in terms that can be understood.
Goedemiddag. Thank you all for being here. 谢谢大家今天来，还有看直播的观众朋友们。Now, to understand a society, we need all kinds of statistics. So, for example, we might ask a question like, how long on average does it take to finish a PhD? Or what is the vaccination rate of the Netherlands? Or kind of how happy are the Dutch PhD students? Most of the time, we will not have the information of the whole population, but only a sample of it. And if the way you collect the sample is related to the topic you're interested in, we may have a problem of selection bias. So for example, like if only happy PhD responds to a survey, you might overestimate the happiness of all the PhD. Then in order to solve this kind of problem, in a classical way is that we draw a probability sample. That is to say that suppose this is a population we are interested in, and we assign every person a probability of this, and we try to draw our sample according to this probability, so that in that case we can guarantee more or less how representative our sample is. But this kind of sample most of the time are already time consuming, and you really take lots of effort to collect maybe just a little bit of a sample, although the quality is very good. Now, nowadays we have all kinds of sample that's called non-probability sample. So it's on the contract to the probability sample. This kind of sample might or might not from the probability, but we do not know it. We just happen to have it. For example, maybe you put an online opt-in survey, you put it just on the website and ask people to fill in. You do not know like who are willing to fill in or not. And you might have some problem of a selection bias. So you do not know if the data is representative enough or not. But these data are very attractive because they usually come very cheap and you usually can get a large amount of data easily. Sometimes you don't even need to do a survey. You can do a web scrap data from social media. You can just look into PhD's, now call it X or Facebook, and see if they're happy or not and collect all the data of it. Yeah. So now the question is, if we're trying to use all this non-probability sample, how do we make it more reasonable or help us to get rid of this selection bias issue? One of the often way we will to solve this problem is by weighting. So we assign every unit inside our sample amounts of weights. For example, if you think this person has a smaller chance to be included in the sample, then we will give it a larger weight. Like on the right-hand side, we weight it as 8. You can kind of more or less understand it as this person actually representing other 8 similar persons. And if a group of people is overrepresented, like happy PhDs, then we will give it a smaller weight of it. Weighting has long been used for quite a long time, but because of all the data you available at hand, you will need to new methods to construct these weights. So in our first paper, we proposed a pseudo-weighting methods. And this method is especially useful for large inclusion of a non-probability sample. This is quite often seen in statistics Netherlands or lots of agencies because they just have too much data. And we combine the information of a related probability sample with the non-probability sample we're interested in. This probability sample does not necessarily have the target variable we're interested in, but they share some common variables to each other so that we can use this common variable to see like which group of people may be underrepresented or overrepresented. And in our framework, we allow all kinds of propensity estimation methods to be included inside. So if you're statistical people, maybe you're familiar with logistic regression or all kinds of machine learning methods that estimate probability. You can easily plug in our framework and use it inside the framework easily. Then finally, we discuss uncertainty, so-called variance estimation in bootstrap ways. Now, given this framework, we actually will run into many practical issues that make all the estimation more difficult. So in the later 3 papers, we talk about 3 different challenges that you might encounter and trying to solve it, maybe not always exact answer. The first one is that since you can use all kinds of models, then which one is the best? Well, in statistics, we have like all kinds of model evaluation way. You maybe think about AIC, BIC, but does it really fit into this framework? Does a good indicator for regular model performance really can tell me which one gives the best estimated population mean or total? This was a question we're trying to solve in the second paper. In the third paper, well, often we have a problem called imbalanced sample. So because the non-probability sample is easily to be very large, and we compare with a small probability sample. If you need to do an estimation combining both of them, then you have an imbalance that one of them is just too large. What exactly is that? Like, assuming you're a machine, trying to tell the difference from cats to rabbits. But here are your training data sets, and most of them are just cats. So if you're a lazy machine, maybe you just get everything guessing as a cat, so you can get a quite good result. But in the end, the machine does not really learn what is about the rabbits. So to solve this problem, we try out also lots of methods in machine learning as well, and fit into our framework. And finally, in our last paper, this is called something like small area estimation. So think about the vaccination cases. Often we do not only interested in like how is the vaccination rate in the whole Netherlands, but also in each area or each age group, how much vaccinated they are. And a model you fitted for the population mean or total actually not always be suitable for every small area. Because you might have some problem, for example, this area just have too little people for you to get a reliable estimate, or they can actually use some information given the area they are in. So in the fourth paper, we combine our framework with the small area estimation model and try to see what should we do and maybe some trade-off we should make if you want your small area estimation as good as your population estimates. Okay, this is it. Thank you very much for your attention, and Yarmar Cat.
Can I please ask you to also give a presentation about your thesis?
I declare that this thesis is my own work and that during my PhD program, I operated according to the principle of science integrity, honesty and scrupulousness, critical attitude and transparency, independence and impartiality.
Thank you very much. Okay, then it's time to go to the committee. Thank you again, committee members, for joining this session. And our first opponent is Professor Dr. Van den Brakel, and he's a professor of survey methodology at Maastricht University. Professor Van den Brakel.
Esteemed doctoral candidate, dear Anne, first of all, congratulations with finalizing an impressive piece of work. I read your thesis with great interest. It also raises a huge amount of questions, and I'd like to start with asking a question concerning Chapter 5. In Chapter 5, you studied two estimators that are used in the context of small area estimation with non-probability samples. And I'm a bit surprised by the choice of these two methods. And I would like to ask to give you a motivation why you particularly choose these two estimators. But before you answer this question, please let me summarize my objections against the two methods. The first one is iterative proportional fitting, which has a major drawback in the context of small area estimation. It's basically not a model, but an adjustment technique. And that doesn't help you to borrow strength from other domains or statistical information from other domains. It also has the drawback that you cannot use auxiliary information other than the domains that you include in the table. And in the case of small sample sizes, the method becomes very unstable and it cannot handle empty cells. And that is typically the situation that you avoid in the setup of your simulation and also in your application, so you do not face these issues. The second method is a Bayesian approach proposed by Van den Dijken, who proposed a model that accounts for complex sample designs by incorporating the sample weights in the pseudo-likelihood function. I admit I haven't read the paper because it's behind a paywall, but my interpretation of this method is that it is intended for situations where you don't have auxiliary information but only sample weights. And you propose a two-step method. First, you use auxiliary information to estimate the pseudo-weights, and then subsequently you use these pseudo-weights in the model proposed by Van den Dijken. But isn't that an unnecessary, complex and inefficient approach? Because you can also use this auxiliary information that you put into your, to calculate the pseudo-weights directly into a unit level model for small area estimation for your target variable directly and fit this model to the non-probability data at hand. And then in the second step, you can make predictions for all population units and get your estimates by aggregation. And that would solve both the small area estimation problem and the selection bias of the non-probability sample. And I think that is at least as good as the two-step approach you followed, or do you think that you still have a better performance with this two-step approach? So in summary, can you motivate the choice of iterative proportional fitting and this Bayesian approach?
Yes, highly esteemed opponent. Thank you for your question. I can talk a little bit about the story of this paper. So when we were doing this research, other research actually, we found that IPF, iterated proportional fitting, performed quite well, even it's just a simple methods. And I think might be important to point out that when we try to do small area estimation for non-probability sample, vs when we just simply do small area estimation, when we have a non-probability sample, we more often have a large sample. So I would say the zero cell problem will relatively smaller compared to normal setting. And also because we are looking at non-probability sample. So the inclusion is a very important thing to consider inside this process. Now, when we talk about for the Bayesian model, I first fit the selection mechanism inside the model. The auxiliary variable will have a larger coefficient in a sense when they really difference between non-probability sample and the probability sample. But if this auxiliary variable directly go to like prediction model for your target variable, you only look at the difference, how much it affects your target variable, but maybe not that much regarding to the inclusion. So that I think that will be the choice that why we would need to first consider the inclusion, then we consider the model fitting or the prediction model. Yeah, and IPF, it's, well, I'd say before we found it quite useful, so we included it in the paper. And I have to admit, Bayesian is just my personal interest. And it shows very good performance when it's just using design weight. And for me, I'm quite curious because design weight is not always exactly the same as the weights we constructed. So that's why I put it in the paper and try to see if the weights have some variation because it's I constructed, then how performance would it be? Yes.
I can take that argument, but I don't think you can call it small area estimation, as you basically admitted yourself. Yeah, and concerning the Bayesian approach, I think you can only lose information if you do first modeling the weights and then put these estimated weights in a Bayesian model compared to directly using the auxiliary information in a unit level model. But yeah.
Thank you.
Yeah, you can still continue with another question if you like.
Okay. Another drawback of iterative proportional fitting is that there is no closed form for a variance estimator. So, and in your simulations, you focus on the situation where you know the entire population and you draw small samples out of it. So you can estimate, or you can calculate the true mean squared error. But how should we estimate the uncertainty in practice if we don't know the population total, or if we don't know all population values? And in particular, how should we account for the additional uncertainty that we estimate the margins with this pseudo-likelihood approach instead of knowing the exact population totals?
That's a good question. Well, Bayesian in general has a easier way to estimate variance, but the IPF, it's rather difficult, it's true. I did not really look into that, but I think the method we tried to do in the first paper, so we create a pseudo population and do everything of it. If I'm going to trying to look at the variance, I think this might be the way I'm going to try. So I create a pseudo population based on a non-probability sample, and then do all the step, small error estimation and blah, blah in the end, and repeatedly and see how the variance will go. But indeed, that's a difficult question. Yes. Thank you.
Thank you very much. Then we move on to the second opponent, Dr. Struminskaya from Utrecht University. She's an associate professor there at the Maths and Statistics Department. So, Dr. Struminskaya, can I ask you to continue the conversation?
Esteemed doctoral candidate, dear An-Chiao, I would also like to congratulate you on the excellent dissertation. I found it written very clearly. You explain difficult concepts very well, and it has high applicability. My question is about chapter 2. So you basically say that you can classify administrative data of, for example, firms that send their surveys way too late, or vehicles that are not passing through the garage, for example, as non-probability. So I'm wondering why? So would it not be similar to non-response in a probability-based sample? And then, if so, what amount of non-response bias would make it comparable to a non-probability, or is it about inclusion probabilities? So help me out here.
Yeah, exactly. Oh, hi, the esteemed opponent. Sorry, it's my first time. Yes, I would say like missing data problem is very close to selection bias. Maybe a little bit different is that if you have selection bias, you have nothing with that person, and missing data, sometimes you have a little bit of it. But the problem itself is really similar to each other. And if you have the whole list of the card, for example, and then only part of the answer, if the rest of the people, you still have the auxiliary information of it, I would say that you can still use some kind of missing data problem, is for sure. But if you do not know them, or if you don't have strong enough auxiliary variable in a sense, you only have the auxiliary variable with those already come to garage. And I would say it will be better if you compare with a probability sample. So it quite depends on what kind of information you already have, and if you just have few empty cells, it's definitely very straightforward. Just use missing data or imputations methods, and I would imagine the result would not differ too much as well. So yes, it's indeed a very close topic to each other.
So basically it can be used not only for non-probability, but for any sorts of data, your method.
Yeah, that would be great. But here we have lots of missing data experts. But I would say for missing data problem, if you have a cell missing, like only part of it missing, maybe this method is not that straightforward. Maybe mice is better. And the idea and lots of things is really related to each other. So I also learned a lot from missingness literature to use it in my studies, because for example, they also have all the ideas of weighting, imputation, and trying to model the inclusion, model the target variable you're interested in, and combining both of them. So yeah, that would be a goal maybe.
All right.
Thank you.
Thank you. Should I continue? Yes. Another question is about Chapter 3. So I was wondering, what was your motivation for choosing the data sets? So you have the election data from the survey package, you have the iris data, and one from sampling package. So they're all kind of example data sets. So why didn't you, for example, use data from probability and non-probability comparison studies?
Yeah, that's a very interesting question. So every time I try to simulate data or try to do a numerical proof of it, I kind of feel like whatever data set I generate, I kind of assuming it's a representative sample as well. So I hope this sample will be, the result from this data set or this sample will be able to inference to the rest of the sample in the world or such. And that's quite difficult, actually. You did not always have a linear model inside your data set. And how should I generate a model? If I generate this way, would the other people think, why you did not do it that way? Or in practice, it's not true. I think the easiest way is just go through some real data sets. That is, it's happening somewhere inside the world instead of I generate it, and then try to see if the result I get is more or less the same in different kinds of data set. And the reason I choose from data package is just because it's easy to get and it's already public, so I can easily download a data set and people can easily repeat my research if they wanted to look into it. And yeah, that's most the reason.
Okay, thank you.
Thank you.
All right, then we move on to our third opponent. That's Dr. Fink, who's an associate professor of dark data science, which is an intriguing title, but who will now, at Utrecht University, but he will now turn to this specific thesis, of course. Dr. Fink, please.
Dear esteemed doctoral candidates, dear An-Chiao, you've written a very nice dissertation, and when I first laid my eyes upon it, I was a bit scared about the title, but luckily for me, it's almost entirely about some form of missing data problem. So, about your title, correcting selection bias in non-probability samples by pseudo-weighting, it came over to me as trying to tidy up your garden during a typhoon. So the input data will always come from some bias process. So let's say that I'm trying to apply this in practice. How confident can I then be that this bias is really corrected and not just simply made to look very pretty with some statistical makeup?
Yeah, I mean, how can I correct, how do I know if I correct for bias? Yes. That is exactly the problem I'm trying to solve in the second paper. It's very difficult, especially when we, well, every question is difficult, yeah. When we try to do all the application, often we run into a problem that if we correct for them, we also do not know if the answer I got is reliable or not and such. So often we need to do in a safe setting, like simulation. I know what does the whole population look like, what does the true answer look like, and try to estimate it again and again to see how much time, if I really get a correct or good enough answer out of it. But in practice, it's still quite tough because most of the time you only have one sample, one non-probability sample, and maybe another probability sample. And you just try to make your best out of it, and hopefully in the end the answer will be better. I guess it will be more or less two aspects of it. One aspect is that from the statistician aspect, I feel like I'm kind of a chef. I open up the fridge, what ingredient is inside, and I try to make a good dish out of it. So if I know, or if I assume some kinds of belief, sometimes it's a distribution, sometimes it's a probability, and then I try to make the ingredient out of it, so try to make my statistic based on the data I look at. Of course, it will be even better if I know my guests who are eating this food, which is a domain expert. If they can tell me that, in Taiwan we like to eat sweet fruit, and then can I make the statistic accordingly that more close to correct for the bias aspect, then it will actually close to one of the performance indicators. So if someone can model the target variable well, it can more or less tell me whether the result I get is similar to the result from your modeling the target variable. But still, in the end, most of the time, we will not be that sure whether this is a result or not. And if you're lucky, or if you're in an interesting scenario like election, you will see your answer after the election. You'll see if I run an online survey asking people who are you going to vote and try to correct for them. After the election, you will see your answer, and then you know how you do in the model. That might be one choice as well. Yes.
So, unfortunately, you have no fix for missing not at random yet.
Yeah.
Okay. I would like to continue about the fourth chapter in your dissertation,
Yes.
where you spent quite some attention on SMOTE, technique based on synthetic values. I have a couple of questions related to data synthesis given the scope of your dissertation. You claim to find promising evidence that synthetic data in the form of SMOTE can be used to improve estimation in your case. I'd like to do a thought experiment. Given the increasing importance, you might say, of privacy, do you think that we should not flip the default in official statistics? That is, should we not release and analyze synthetic values rather than real ones?
Yeah.
Unless there is a very good reason not to. So can you reflect on that?
Yes. Oh, I think the synthetic data, how to create, how to use it, and all the, no matter privacy issue or usefulness issue, is a very big topic. And I also know when I work on this one, I also talk to people in CBS who actually work on the synthetic data. And yes, it will be very exciting if we can just release a synthetic pseudo population, and then people can do research on it or do everything on it. But also, along the way I work on this paper, I found that little attention, or at least during my research, not many attention about the statistical validity. Some people might say that, okay, I have an estimated mean or total of this synthetic data set is the same or close enough to a real data set. And how do we make sure all the data set is always useful is tricky. And so if people are quite professional with synthetic data, you might find that SMOTE is rather simple methods, because I basically do a linear combination about the neighbor units and try to create a new one out of these units. So kind of assuming that linearity between units or is symmetric enough and such. And the reason that we go through a simple methods is totally because, in a sense, we can prove the statistical validity out of it. So because it's just a linear combination, I can know that how my variance goes, how my total and mean goes, and that's why we choose a simple methods and also use it in this paper. So yeah, this is a very interesting and big topic, and hopefully more research on it in the future.
Okay, thank you.
Thank you.
So how do you then, if you use some methods to generate synthetic cases, even though it's very simple, as you say,
Yes.
In the concept of all the misalignments that may already happen in the theory that you're working with, you want to go back to the answer, you want to go back to estimating the population. So isn't then a bit of an ontological difficulty? Are we still estimating then reality, or are we inducing more and more fiction into our model by just focusing on the synthesis in this case? Well, let me rephrase my question. You said you're talking about statistical validity. So synthetic values, as you know, are very closely related to missing data. Well, missing data field by Rubin started as synthetic data. And in missing data, we have something that's called congeniality. It's like how much are my analysis model and the imputation model soulmates? How much are they in alignment? Is there also something, in this case with SMOTE, that we should consider, some synthetic sampling congeniality, in the sense that neighbors really reflect a close match to what they should be or shouldn't be?
Indeed, we did not directly look into how close the generated sample is to the probability sample. In our case, it's a probability sample. But I think most of the sample is already foreseeable, especially SMOTE, because you know how they generate it. So, for example, you can, if you have a histogram out of it, the sample is more or less inside the histogram, maybe more smooth because you have a linear combination about each neighbors. And I think it tells most of the story. of the similarity, so we're not too surprised, I would say. If you have large enough sample, it will be. If you have more difficult, like GANs or a tricky way, maybe you need to look at a distribution or a relation between things. But I think especially for modes, I can quite straightforward foresee that the generated sample is more or less the same inside this distribution.
Okay.
Yes.
Thank you.
Thank you.
How am I in my time? Oh, one final small question. Okay. So, reading this chapter, it got me really enthusiastic about synthetic values for solving this problem. And so it solves the problem of imbalance in your case to some extent. And then I thought, why not skip all these difficult steps in all the previous chapter, and why not create a synthetic population? Why not do mass imputation? And wouldn't we then not have the same realization and same results as your dissertation?
Yeah, that's a very missing data problem. So we can think together how we do mass imputation if we want. For example, we have a non-probability sample. We have auxiliary variable and a target variable. If we only have the other probability sample with auxiliary variable, which means that I need to fit a model based on non-probability sample, and then use this model to impute a probability sample. Yeah, that will be one kind of mass imputation cases. But the problem is my non-probability sample is selective. So I'm also not sure if the model I get from non-probability sample actually reliable enough in the probability sample. And I would say the other question is that non-probability sample are usually quite large. So you use a large amount of data, generate a model, and input a small probability sample. And the variance will be quite large in a small sample rather than a large sample. And you throw away a lot of sample, lots of units in the non-probability sample. Might be a little bit wasted. So you will be constrained like having a large variance in the probability sample. And then if you're interested in more than one target variable, I want to know like whether they get vaccinated and where they live and how is the age of it. You need to impute everything in that small sample. So that means you need to do a couple of modeling again and again and impute it inside a sample again. So I would say in a perfect scenario, so in a perfect scenario means that I know the correct imputation model, or I know which variable I should include it, and I go to impute it. I might have a good estimate, but with large variance, but would not be to matter. But if not, I would say weighting may be more straightforward for people just make use of this large non-probability sample. Yes.
Okay. Thank you very much for that.
Thank you.
Thank you, Dr. Vink. Let's move on to our final opponent. That's Professor Dr. Jeroen van Munt, who is the Professor of Statistics for the Social Sciences in our own school here at Tilburg University. Jeroen.
Well, thank you, Chair. Esteemed doctoral candidates, also read your thesis with pleasure. It was really nice, really nice thesis. Your thesis is about resolving a practical problem, which is among all relevant for CBS. CBS is experimenting with the use of non-probability samples because of various reasons that you also mentioned. It's cheaper, you're not so much restricted by response burden kinds of issues, etc. And your thesis looks especially to a situation in which there is some overlap between a non-probability sample and the probability reference sample, and where the non-probability sample is really large compared to probability sample. So that was my interpretation, so that you start with a practical problem. And given this practical nature of the problem you wanted to solve, I noticed that you didn't present real data applications. And if you do so, then you already answered one of the questions here. You are using the real data sets again to have a kind of population, a more realistic population. So we are using them again in a simulation study, basically. So I was wondering why you didn't apply your methodologies to real data from CBS, I would expect, because your PhD was sponsored by CBS, so I would also expect some results which are relevant for them. It would be interesting to see whether it makes a difference if you apply your methods to CBS statistics, maybe only for sensitivity analysis. That doesn't need to be immediately the official statistics for the Netherlands. Did you apply the method to CBS data? Maybe you did, and you didn't report it in your papers. Can you tell a bit about the link with CBS applications?
So far, that only in my first paper, we use the data sets from the meters thingy. So we do not use the exact application yet. One side, I would say maybe it will be a future interesting work is indeed. And I can do like whatever non-probability sample and apply on it. But again, we run into the difficulty at how do we say if this one single application really give a reasonable answer. So that's something we keep repeating, think about it, and we did not find a good enough answer to say it. That's why we didn't just use the application and show the statistics, but try to do it more safe way, draw it repeatedly and see the answer of it, see if it's close enough and such. But maybe future. I'm looking at the CBS before here. If I successfully convince them, and maybe hopefully one day they will use my methods in official statistics. But you know, like they are important to communicate all the statistics. They really need to make sure all the methods really reliable enough, and maybe long tests until they really become use cases in the application. So maybe someday, yes.
Yes, I fully agree that really applying then already now for obtaining official statistics is maybe a step too far. And you say, I'm looking for the truth, but I can also think about something about more like a sensitivity analysis. You can think about, so you compare different approaches, and for one of the things you would like to know is that doesn't matter, that does your specific way of getting the propensity scores compared to the approach that you are kind of improving. That doesn't give really different results. You do it in a simulation study, but it would also be nice to see how it works in a real data application. Or am I wrong about it? Whether that makes sense?
I do wonder, what did you see between the real data analysis and the simulation? Because many of my simulation is actually based on the real data sets, but I just treat it as a known population and do it repeatedly and see the answer between the, I assume, population and such. Yeah.
The moment that you're using a real data set in simulation again, you are creating also non-probability samples, using a certain mechanism. And you still don't know whether that's a mechanism that is in agreement with how non-probability samples occur.
Yes.
So that's the kind of feeling I have. That's kind of point missing there.
I get your point. Yes, that's a good point. In one of the simulation, I did not generate the non-probability sample at all. I use the data set and look at one of the variable is actually binary. So if this binary variable, if it's 1, I treat it as a non-probability sample. If it's 0, I treat it as I do not see it. In this case, you can see the result and blah, blah. And this one, I think it's a performance measure one. So I show the calculated error. You use a non-probability sample and correction and performance measure of it, and also a true answer, like the whole sample of it. Yeah, but in that case, we indeed show the result of it. So because it's a variable, and this variable is not included in the model, although it's a whole data set, so other variable is related to this variable, but I did not use it for modeling, but just treat it as kind of an indicator to see if it's a non-probability sample or not, and do other things. Yes, that's indeed an interesting thing. So, sorry. In practice, like we also mentioned in the thesis that sometimes the inclusion might not even be a probability as well. You just happen to be, it's a deterministic cases, or all kinds of possible occurrence of your data sets. Although we assuming that the non-probability sample is in essence a probability sample, just we do not know how it is included, and we do all the estimate and assumption. But even if the data is not really a probability sample, it's deterministic. During the modeling process between the probability sample and the non-probability sample, you're kind of modeling the discrepancy, the difference between two samples of their distribution. So, for example, you can already see maybe the gender proportion is different or age proportion is different, and this kind of discrepancy, this difference, if you already minimize it, it can give you already a better result than doing nothing. Yeah, so even if your data is not generated in the model or in a probabilistic way, I would say applying a good method will improve your result. Thank you.
Okay, thank you very much, Professor Van Munt. Given that the beetle has not yet shown up, we have time for a second round. So I'd like to invite Dr. van den Brakel again for a question.
Esteemed doctoral candidate, dear Anne, there are many methods in the literature to draw inference from non-probability sampling. Your thesis focuses on methods that are based on pseudo-weighting. Other approaches are doubly robust estimation, matching techniques, or modeling and prediction of the population units. And a motivation for your choice to focus on pseudo-weighting is provided, I think, in chapter 2 on page 13, where you give 4 advantages of pseudo-weighting methods. Now, to put this approach in the right perspective, I would like to invite you to mention a couple of disadvantages of this approach.
Yes.
And is pseudo-weighting always the most appropriate approach among all these methods? And maybe also in line with the questions of Professor Van Munt. What is your honest opinion to which extent non-probability samples can replace probability sampling with the purpose to produce official statistics at Statistics Netherlands?
Yes. Yes, exactly. That's a highly distinct opponent. The first one. Oh, yes. Thank you. Yes. Weighting methods in general is infamous for large variance. So if you have certain groups that have very, very low chance to be included in your sample, you have no choice to assume a unit a large weight. For example, if you hardly can find a Taiwanese in the Netherlands and you happen to invite me to a survey, I might weight as 1,000 or something. And my opinion become really important because I represent a lot of people. And if Taiwanese have a large variety, or our opinions are very different, you actually run into the risk of giving me too much weight. So that would be one thing that people who do not like to use weighting. And what else weighting has a problem? Oh, I personally quite like it, so I need some time to think about it. But I can go first for whether it can be used for official statistics, because I believe it's more or less why they wanted to look into this topic in the first place, because I think most of the agency want to cost down. And also, if it's a non-probability sample like web scrap data, you can get it in a very cheap and very fast way. So maybe our statistic can produce even daily or even a faster time if the source or the correction is reliable. I don't know, like how far the future will be when we really able to use non-probability sample directly to use as an estimate. I would say, well, at least in a safer case. For example, Bella mentioned like how fast you fill in a survey for the companies. If they repeatedly have some same patterns, some companies always fill in faster, and some company always fill in slower. And the size of company is rather stable. In this case, maybe you will have more confidence about what kinds of correction methods is more reliable, and we can more safely to use this kind of information to produce statistics. But if you just have a very random non-probability sample, well, random is a bit overused, but you just have some online survey and you don't know who exactly is filling in, and every time might be going to different sources, different kind of people, the process might not be the same as before, the reliability of this non-probability then would definitely be more difficult. So I think we also have colleagues working on like a repeat fill-in, this kind of a non-probability sample. I would say they might be go faster, go into the real official statistics space steps. Yeah. And I'm also looking forward for that day, but I don't know how far we are to like always get the most correct answer. The research is never done. And yes, I will happy to do more research and always look into this kind of problem. Yes. And back into the problem of weighting. Well, yes, I think one of the most straightforward competing methods is imputation. So you modeling the target variable or you modeling the inclusion. And some people nowadays, they're really popular, that so-called doubly robust. So you compare these two models together. You have information for the target variable you're interested in, and you also try to look at the difference between the non-probability sample and the probability sample and combine information of it. If you're lucky, one of the model works, so the total estimate will not be too off. So people would say that the weighting methods does not really consider the target variable you are looking at. That might be a drawback, so that people want to use doubly robust. Also, if you think about the essence of selection bias, so selection bias comes from the relation between the target variable and the inclusion. Like a very early example, I talk about maybe happy PhD, more willing to fill in the survey. So you overestimate the happiness of a PhD. And in this kind of aspect, to think about it, it's definitely reasonable to modeling both of them together, because they all play a role inside this bias thing. Yeah. So if you have information of a target variable, you know which model is good. Then also included the imputation model to say, or the model for target variable, and to combine it all together. I believe will be better than the weighting methods. And indeed, I did not directly discuss this part of things, but it will definitely be an interesting future research. I hope this answers.
Thank you very much, Professor van der Bakel. I propose we go for a second question to your neighbor, Dr. Struminskaya.
Esteemed doctoral candidate, so now you are at Utrecht University, and as people from Utrecht University know, there's a consultation shop where researchers can come and ask statisticians, methodologists for the advice. So imagine that now I am a researcher who comes, I looked, I saw your dissertation, read the title, Correct and Selection Bias, Non-Probability Samples, and think, well, I have collected some data during COVID times, post-COVID, on Facebook in multiple countries, on behaviors of people. Can I make it representative, is my question. So what do I do with my data now that I have?
Yes. It will be a perfect scenario if a researcher come to me before data collection. I mean, I'm not trying to make you to do a probability sample, but if you, like, for example, you're doing a COVID survey, try to think about what kind of auxiliary variable is already available in, for example, CBS websites. In CBS, you might find a distribution of each age group, a distribution of gender, and how many people live in each town and such. When you're going to collect your non-probability sample, even if it's just an online survey, try to include all these related information as much as possible inside your survey, so that data point, we can use it as a pivot to see, like, which kind of people is underrepresented and how can we correct for this. And if you come to in a later point, you come in with a survey that you don't have much information of an auxiliary variable, that would be indeed very tricky. I would say always the good auxiliary variable always came from similarity to the target you are trying to estimate. So I try to find as much as related information that is reliable enough, or maybe look into other probability sample survey to see if they have something similar to you, so that you can correct for this action bias.
This session is adjourned for deliberation. Please await the committee's return.